Further Maths AS Unit 3 Prerequisites for Hooke's Law, Work, Energy and Power. So the prerequisites we have for this part of the course are first of all resolving forces into perpendicular components, and later on we'll have a look at friction. So for perpendicular components, the key is to remember that forces are vectors, and that means we can break them up into components. So what we have here is a force that's acting at an angle to the horizontal, and we might want to consider things in say vertical and horizontal directions. So we want to resolve or represent the force as two separate forces, one horizontal, one vertical, as vectors. They add up top to tail, and so the two red vectors add up to give us the black original vector. And remember, this sort of process can work in lots of vector situations, so you might want to resolve a velocity into perpendicular components or an acceleration or whatever. So how do we do it? Well, here's the situation we've just seen, and you'll notice that I've put the hypotenuse, the opposite and the adjacent, which might give you a clue as to what we're going to use. You've probably worked it out already anyway. So the force itself I'm going to call F, the vertical component FV, and the horizontal FH, and we can just use trigonometry. So FV over F is sine alpha, and then we can work that out. So FV is F sine alpha, which is 7 times sine of 30, which is 3.5 newtons. And for the horizontal, that's the adjacent, so we have FH over F is cos of alpha, and then we can work that out, which gives us 6.06 newtons to 2 decimal places. We could of course use Pythagoras for the final force once we know what F is and what FV is, or FH, so I've just popped that calculation in there as well, and of course we get the same answer. So moving on, we also sometimes have to deal with parallel and perpendicular components. So if we have an object on a slope, for example, so that's that blob, and there is a force on it which is its weight, so I've called that W, and that's acting vertically downwards of course. So as before, we might want to split this into components. This time they are parallel to the plane and perpendicular to the plane. So I've labelled them W parallel and W perpendicular. Now notice that although we can sort out the vectors this way, in fact those components are acting from the object. So we use the triangle so we can use trigonometry on it, but we remember that we have to consider it acting on the object in the way indicated. Now we have an angle of 20 to the horizontal, and using right angle triangles we can sort of chase the angles round, and we can pop angles into that triangle ready for dealing with it. Doesn't matter whether you use the 20 or the 70 in the next calculation. I've chosen to use the 20. So in this example we have a weight of 12 newtons, and we can see that the weight parallel, W parallel, is opposite to the 20 degrees, and therefore it's 12 sine 20, 4.10 newtons, and the perpendicular component is the adjacent to the angle, and so that's 12 cos 20, or 11.28 newtons. We also need to have a quick look at friction. So friction opposes motion between two bodies, as we know from our ordinary lives. It is independent of the relative speeds of the bodies. It's proportional to the force involved up to a limit. It acts parallel to the motion of the object, and the force is less than or equal to mu r, where F is the force due to friction, mu is the coefficient of friction, and R is the normal reaction force between the bodies. We'll have a look at three situations involving friction then. So the first one is when the body is not moving and nor is it about to move. That'll make sense in a sec. And notice on the diagram mu r is the frictional force, as we saw on the previous slide, and in this situation r is the reaction force of the surface on the object, and that's equal to the weight because it's in equilibrium vertically, so the reaction force must be equal to the weight, or the upward force equal to the downward force. So at this stage there is a force on the body, if you like, trying to pull it along, but the friction is enough to stop it moving. In the second case, it's about to move. So at this point there is a force on it which, when it gets a little bit more, then it's going to be enough to pull the object along. And then once it's moving, then there is a larger force on it and it has some velocity. In fact, it's accelerating and so on. So in the first instance, the frictional force is equal to the pulling force, or the force that's not pulling but trying to pull. In the second situation it's also equal, but it's on the point of getting to the third situation where the pulling force is greater than the frictional force, and therefore it accelerates in a horizontal direction. That's what that double-headed arrow means. So because F3 is bigger than F, then F3 minus F is positive, and that equals mass times acceleration. Therefore acceleration is the difference between the pulling force and the frictional force divided by the mass. Now the forces are getting gradually greater, as the discussion has already indicated, and the force F2, which is when the object is about to move, is called the limiting force.